This is going to be a video key for solving the problems having to do with the monochrometer terms. In the previous video, I gave you some explanations of these terms. And if you're missing those equations, please go back and watch those videos. Solving the problem this way is going to give me a little opportunity to explain some of the things that exist in real problems. Normally when you buy a diffraction grating, it is going to be defined by how many gratings per millimeter. Remember that the smaller the diffraction grating size, the bigger the dispersion of the light is going to be, based on that slit width. So what we really need to know when we're solving for linear reciprocal dispersions is what is the size of the slit width d. We know that the linear reciprocal dispersion is going to be equal to d divided by nf, where that is the slit width and that is the focal length. This problem gives us a definition that says that 1 millimeter contains 2,400 slits or gratings. That means that each slit would be that 1 millimeter divided by 2,400, meaning each slit is 0.000417 millimeters wide. 1 millimeter contained 2,400, so each one is 4.17 times 10 to the minus fourth millimeters. Or if you remember that there's 1 times 10 to the sixth nanometers per millimeter, that means that each one of these slits is 417 nanometers wide. That makes solving this problem fairly easy then. D to the minus 1 is simply going to be 417 nanometers divided by the focal length, which was defined as the problem at 200 millimeters. Meaning the d to the minus 1 in this problem is 2 nanometers per millimeter. And that is a good set of units because we want to know how many nanometers of wavelength is sliding through each millimeter of exit slit width W. For example, in question 2, calculate the delta lambda, or the bandwidth, that would be selected by a monochrometer with the above d to the minus 1 at a focal length of 200 with a 3 millimeter slit. Very simply, the delta lambda is going to be W d to the minus 1 the slit width is defined as 3 millimeters. This is 2.09 nanometers per millimeter. That cancels. The bandwidth getting through a 3 millimeter slit is going to be 6.27 nanometers. Finally, calculate the slit width W that is required if we want to resolve the doublet, the two peaks that are only separated by 0.6 nanometers. Resolving that requires a bandwidth that is half as big as the delta lambda getting through the slit. So we define that as delta lambda resolved is equal to 2 WD to the minus 1. Again, all you have to do is plug it in. We're trying to resolve a 0.6 nanometer difference. And we know the d to the minus 1 is still 2.09 nanometers per millimeter. So to resolve those two peaks, you have to go down to a very narrow slit width. So the exit slit width is almost 0.1 millimeters.